Okay, elastic potential energy, example 5. So in this one, we've got an elastic spring of natural length 1, so L is 1, modulus elasticity 20, has one end attached to a fixed point A. A particle of mass 2 is attached to the other end, so the mass of this particle here is 2, and is held at a point which is 0.8 below A, so this distance here is 0.8. The particle is projected vertically downwards from B with a speed of 2. So from here, it's projected down with a speed of 2. Find the distance it falls before first coming to rest. So if we say this is where it comes to rest, if it's come to rest, then the speed must be 0 at that point. We'll also say take this as our place where potential energy is going to be 0. Now, if we've got this distance is 0.8 and it's got a natural length of 1, then that means as it's being projected down, at the moment when it's here, it must be being compressed because this is shorter than its natural length. So it's being compressed, so when it's coming down here, it's going to come to its natural length of 1 after 0.2, and then it's going to extend for a bit. So this distance here must be 0.2 plus x. And this is going to be a conservation of energy again. Energy at the start equals energy at the end. So at the start, this is slightly different because you're going to have 3 energies at the start. If we start, this is where it's starting, remember here. Start, end. So at the start, it's actually going to have kinetic energy because it's starting with a speed of 2. It's going to have potential energy because it's above the end point. And it's going to have elastic potential energy because remember at this point here it's been compressed to a length of 0.8, so it's got 3 energies at the start. So if I work out those 3 energies now, so kinetic energy, half mv squared. Remember the speed at the start is 2, so if I put 2 in for that, is going to be 4. If I work out the potential energy, mgh, so 2 times g times the height. Now remember, this is where potential energy is 0. At the start, this distance here is the height, so the height is 0.2 plus x. Expand that, and you get this. Okay, so here's our 2, and then we've also got elastic potential energy. Okay, so you put those ones in. So lambda from the question is 20. The extension, now just be careful with this, we go back to the diagram again. We're talking still at the start and we're talking about the elastic potential energy at this point. So at this point, this is the spring and it's been compressed to 0.8. So the compression, if the natural length is 1, the compression at this part of it is 0.2. Okay, so the compression is 0.2 squared all over 2 times 1, which comes to 2/5. So there are 3 energies at the start. Now at the end, it's just going to have 1 energy, elastic potential energy, not from compression this time, but because it's being stretched at the end. So this is going to be the same formula. Put the numbers in, so same modulus. We don't know what the extension will be at the end. So we'll call that x over 2 times 1. So that's going to be 10 x squared. And then it's a case of equating all these. So energy at the start equals energy at the end. Okay. So, sorry, try and go straight again. These were our energies at the start. What have I done then? 4 plus, sorry, 2/5, lost where I was then, equals the energy at the end, which was that. Rearrange this and you get that. Factorize that and you get these 2 answers. So obviously you're going to take the positive answer, and then that means it must fall 2.32 plus 0.2, which is 2.52 meters. Okay, if we have a look, that's why, because it's fallen all this distance, you add on the 0.2.